Hi, this is Ruslana. Here's my final project on 15463, 3D structured light with gray, binary, and XOR codes. Here's kind of going to be the gist of what I'll be talking about: background, implementation, results, things I wish I did, and then that'll be it. So first for background, so 3D structured light is typically a method that's used to reconstruct some form of 3D scene. It involves a projector and a camera or multiple cameras that will take photos of the patterns that are being projected from the projector onto a scene. And because you know what those patterns are, you can take the photos from the camera and infer some sort of information. So in one case, one application is like scanning Michelangelo, this statue here, with a laser. What I'm going to get to a little bit later is that the projector can also act as a form of reverse camera because you know exactly what kind of pattern you're going to illuminate onto the scene. So you can create point-to-point correspondences, and these points will follow epipolar constraints. And you can use essentially like stereo geometry to solve problems. The most naive case of structured light is column illumination. You illuminate one column at once, and this is very easy to form a point-to-point correspondence because you know exactly what column, but this is impractical because it takes a huge amount of images. So what's nicer is that you can use gray and binary codes. This hugely alleviates the number of images you need to take. It's essentially log 2 of the amount of columns you have in a scene. And it's pretty reliable results. How it works is that you project all these binary or gray code patterns onto a scene, and this way each pixel will have a unique code within the stack that corresponds to its position. To back off a little bit though, there are some more complicated lighting effects and you globally illuminate a scene that can kind of like harm the way that we typically do structured light with binary and gray codes. So something that we don't really talk about too much unless it shows up, of course, in their non-ideal model is indirect illumination. So one certain instance is interreflections, where light will bounce within a scene before getting back to the camera. It's not just to the scene and then back. And then the other circumstance is subsurface scattering, where light will enter an object, bounce around within it, and then exit and hit the camera at a different point than when it kind of entered from. And these things can really affect the decoding process with typically binary or gray code strips. For instance, you can see this bowl. There's this white patch of light that's from like the strong interreflections, and when you shine the binary or gray codes on it, it'll accidentally decode that as on when it's not supposed to be on, and then you can get some errors in your binarization. But thankfully, there's some ways around this or ways to alleviate this problem. So something that was realized is that high frequency light is indirect lighting is invariant to it, so high frequency light kind of acts like a low pass filter in this circumstance. It's more resistant to the interreflection effect, so if you use it, you can decode columns more specifically. And what's nice is that if you XOR two kind of inverse codes together, you can reconstruct what was originally like a low frequency gray code. And this is nice because what this means is you can essentially shine only high frequency XOR codes onto a scene and then XOR them back together to get your gray code binarization. And this alleviates some of the direct illumination effects. So, indirect illumination effects. So implementation-wise, so patterns used, I used gray binary XOR patterns as I mentioned, and as you can see here are some of my decoded correspondences. Blue is minimum and red is maximum, so the smooth gradient indicates that the columns were found in the scene pretty good. As you can, the bottom right here is the XOR, which looks a little bit funky. It's still reliable, but I'll explain more in that in the results section. First, I calibrate my camera. This is pretty straightforward. Just capture, well, I say straightforward, but it took me a very long time. Capturing the chessboard at various different poses, using that to get the intrinsic camera calibration distortion parameters. A little bit more difficult than that is projector calibration. I followed the strategy that was in the Brown University course on structured 3D light, which was on, they suggested following this paper called Simple, Accurate, and Robust Projector Camera Calibration, where you take photos of the checkerboard in various poses, you capture a gray code stack for each one of those, and then with the known positions of the corners from one pose, you can essentially decode where you expect the corner to be in your decoded image, and then estimate a homography for each corner as to how it gets there, or how it maps to the scene. And then essentially with those newly mapped points that you've created with the homography, you can calibrate those, and then that will give you roughly points that you can then enter into the calibration formula, and that'll give you like a projector calibrated intrinsic parameters and distortion as well. And once you have those, it's pretty sufficient to simply use stereo calibrate to obtain the rotation translation vector between the camera and projector points, which goes straight into triangulation, just like with stereo vision. You have mappings between the camera and you can basically just project the ray from the camera center, and then the known point corresponds that you've decoded with the projector. You can back project both of those rays and find the intersection point, and that forms the 3D point, and the Z value there is the depth from your scene. This is an image on the right of the decoded points I have from one to another. Not entirely perfect, but as you can see, most of the scene is captured. The XOR code correspondences were a bit more bumpy. I suspect this is because of resolution problems with the strip width that my camera was able to capture in the scene, but I still looked okay. So as you can see here, I have gray and binary results that are not too bad looking. Those XOR results are missing some of the points, but if you look closely, I think the shape of what I captured here is a little bit less warped than the other two, so it handled like the specularity and stuff like that better, the overall shape of the 3D printed Among Us. And then in this case too, with this kombucha bottle, so it's glass, it's got a bit more going on with it in the indirect illumination realm. The gray and binary results, I constructed more points, but it does look a bit warped. The XOR results were a bit funky, but I do think that the bottle shape is a bit more intact if you kind of like trace out the edges of it. This kind of leads me to what I wish I did next. So one of them, a reach goal was constructing a la carte structured light, and then the other thing was actually completing like the global illumination, like robust noise kind of sensing pipeline, where I could have added more XOR codes and the other form of gray code with minimum strip width codes to create like a self-verifying pipeline. I wish I did that, but it took me too long to calibrate and collect data that I didn't quite get there. But anyway, thank you for listening.